I think number 17 is a cool problem here, guys. They've given you something called an elliptical cone. Now, I drew it from a little bit more straight on of an angle than they did. The weird thing about this problem is every cone looks like its base is an ellipse when you draw it from the side. If you think about that, most cones have a base that's a circle, but only a geometry kid that really doesn't know what they're doing would actually draw a circle and then try to make a cone out of that. That's not really what a cone looks like at all when you view it from the side. But it's important to note here, guys, that even though all circular cones have a base that looks elliptical, this one actually is an ellipse. And they told you here that one of those pieces, this is called the semi-minor axis, is 4, and the other piece, called the semi-major axis, is 6. And they were nice enough to give you this formula right here, guys. The area of an ellipse is AB pi. I like that formula a lot because it kind of makes some sense. If you were to think about an ellipse here, and then this, actually, I think I kind of have this backwards, guys. A is usually the longer piece, and B is the shorter, but it really doesn't matter. They're telling you that the area here is A times B times pi. Well, if you think about a really specialized case of an ellipse where A and B were actually the same length, oh, now you'd be dealing with a circle. So if this was A and this was B, but in this ellipse they were congruent, we would say, okay, that's congruent to that, and we wouldn't call this an ellipse, we'd call it a circle. And instead of calling these pieces A and B, we'd call them both R. So then the same area formula right here would become, well, not A times B, but R times pi, otherwise expressed as pi r squared, which of course is the expression we all know and love for the area of a circle. So that doesn't prove anything here, guys, but it does kind of suggest that, yeah, this formula probably makes sense. Okay, back to it, guys. We're trying to come up with a formula now for the volume of this elliptical cone when the semi-major and the semi-minor axes have a length of 6 and 4, and then the overall height of this cone here is going to be 12. Now, I've told you guys in class to kind of ignore the way they've set it up, and we're going to treat this as a solid along an axis problem. So we'll start right here with our origin with a height of 0, and what are we going to do then? We're going to draw our elliptical cone over here somewhere looking like that, and then we will create the cone out of it by just connecting the vertex to that part of the base and this part of the base. Hey, you know what? I'm going to call that good enough, although I realize now that would have been a solid piece right there. All right. And if I wanted to make this just a little bit more accurate here, guys, that piece that I've drawn right there probably should have been dashed. The axis right here would be inside of the cone until it busts out right here, and then we would see the whole thing as a solid. So, in all of these problems, we've talked about taking slices here, guys, that are going to be perpendicular to the axis. So I'll draw one of them right here. It's like we're cutting a really skinny piece of bread out of this oddly shaped loaf here, okay? And that's what we've got. So what I think we can see right here, guys, is that our cross sections are all going to be, now it's tempting to say circles, and I almost did, they're actually going to be ellipses, because the base that we're dealing with right down here is an ellipse and not a circle. So what we need to do then, guys, is come up with this little formula here off to the side, that our cross sections are all ellipses, and the area of an ellipse is equal to A times B times pi. What we've got to do is name our axis, and most of us prefer to call that the x-axis, although I think it would make sense if you're thinking of your height as 12 here, I think it would make sense to call that the h-axis also. But again, most people kind of like x a little bit better, and what we've got to do then is find a way of expressing this quantity right here, which I'm going to say, I'll go with what I had before. I'll call that B, and then this quantity right over here, which I'll call A, we need to express both A and B in terms of x. Now to do that, I'm going to go focus, everybody, on the values I have in the upper right-hand corner, here and here. For example, the ratio of A to, oh boy, to height, but I just said we were going to use x instead, so you know what, let me call that x. The ratio of A to x at full size here is going to be 4 over 12. Now let me multiply both sides by x here, okay? And what's that going to do? We're going to get A is equal to, and the 4/12 is a 1/3 x. So if I go back to my area formula here that I had in blue just a second ago, we can get started now coming up with this formula as a function of x. And the a right here, right there, a can be replaced by a 1/3 x. So however big x is at whatever particular slice, like for example at this slice right here, whatever the x value is from here to here, this a value is going to be 1/3 of that. Now we need to come up with an expression for b. So let me go back to purple here, and let me do the same thing again. The ratio here, and I'm talking up in this diagram again here, guys, the ratio of b to x looks like it's going to be 6/12. And if we multiplied both sides by x, just like we did before, those x's cancel. And you're going to get b is now equal to 1/2 x. So back to blue now, guys, in my formula for the area of each elliptical cross-section, the b value can be replaced by a 1/2 x. And then lastly, that pi right there just kind of goes along for the ride. Okay, and I think we can probably simplify this, definitely. The 1/2 times the 1/3 is going to get us a 1/6. We've got x times x, so that's going to be an x squared, and then a pi right there. So that's as good as we're going to get that formula, guys. That's the area of any one of your elliptical slices. So as we've said this entire chapter here, anytime or whenever you come up with the a of x formula, the hard work is pretty much over. So now, let's go to find volume. And our volume function is always the same, or our formula, I should say. It's a definite integral of whatever your a of x function is. Now, I guess, yeah, this is one I'm going to do by hand, guys, and it probably is a good idea to leave myself a little more room here. Rather than writing 1/6 x squared pi as my integrand, I'm going to pull out the 1/6 and the pi, and I'm going to write that as a pi over 6 out in front. Those are constants, so you might as well yank them out in front of the integral. And then x squared is all I have left for the integrand, and we're doing this with respect to x. But let's talk about limits of integration. On this x-axis, the cone starts right here at an x value of 0 and ends right here. And if I go back to the original up above, guys, remember we were dealing with a total height here of 12. So that, there we go. So that 12 is going to be our upper limit of integration. All right, I'd like to try to do this by hand. Let's see how far we get. We're going to get a pi over 6 out in front, and that's going to get multiplied now by the antiderivative of x squared, which is going to be a 1/3 x cubed, all evaluated from 0 to 12. Interesting. I'm going to go ahead and put the pi over 6 and the 1/3 together to get a pi over 18. Gotcha. And now I'm really just doing the 12 and 0 into the x cubed. So I'm going to get a 12 cubed, ugly, minus 0 cubed. That I don't worry so much about. And if you don't think you know what 12 cubed is off the top of your head, you're probably right. But let me show you a little trick right here, guys. What we're dealing with here, all right, we can really just ignore that 0 cubed. We really end up with a 12 times a 12 times a 12 times a pi all over 18. Now I'm with you. I don't know what 12 cubed is either, but I do know that I can cancel out a greatest common factor, like for example 6, from one of the 12s on the top and the 18 on the bottom. Dividing a 6 out, this becomes a 2, this becomes a 3. And I do know, as I know you guys do as well, that 12 times 12 is 144, and 144 times 2 I can do in my head. That's a 288 pi all over 3. And I am pretty certain 288, no, dummy, of course it is. It is divisible by 3. I should have noticed this a while ago, guys. In fact, you know what? Get rid of everything I just did there. Sorry, I should have seen this earlier. You can still do a little bit more canceling here, everybody. We can divide this 3 out from that 12. So dividing a 3 out, this 12 becomes a 4. This 3 now becomes a 1, and our life just got even easier. So up in the numerator, 12 times 4 is 48, times 2 is going to be a 96 pi. Gotcha. And then, of course, just a 1 on the bottom. So 96 pi cubic units is going to be the answer that we came up with here for the volume of this entire thing. Now, real quickly, before we close the book on this problem, are we right? Well, I think so. But here's what we can realize, guys. The formula for volume of a pyramid is still 1/3 area of the base times the height, regardless, I'm sorry, that should have been the formula for volume of a cone, not a pyramid, but my point was going to be the same either way. It's still the same formula here, guys, for area of the base times the height. And it doesn't matter whether it's a cone or a pyramid, it doesn't matter what the shape of that base is. As long as you find the area of that base, this formula will work. So let's see, 1/3 times, all right guys, now this base is an ellipse, and if we use their formula here of a times b times pi, that means that the area of that base, I wrote over it now, was 4 times 6, 24 pi. That's the area of that base right there. So I'll put that into this formula now for capital B, 24 pi, and the height of this whole thing was still going to be 12. A couple ways you can do this. I would probably go do 1/3 of 24 to get 8. Gotcha. And then the 8 times 12 is going to be 96. Stick the pi on the end, and there's your volume using geometry. So whether we did it geometrically or whether we did it calculitically, I'm not sure that's a word, using calculus, we got the same answer. Now again, let's be good scientists, everybody. Getting the same answer twice doesn't guarantee that we got it right. If we got different answers, that would guarantee that at least one of them was wrong, if not both of them. But it does provide a good shove in the right direction, kind of a pat on the back, telling you that there's a very good chance now that that answer is correct. So once we look at the solutions manual, I think we'll feel even better about it. All right, guys, so that's number 17 in section 6.2.